Hello, AP Physics C. Today we're going to talk about capacitors and capacitance. And I'm going to start with a capacitor. A capacitor is a device that we use in electronics that stores electrical energy and electrical charge. When we look at a capacitor, the amount of electrical energy and the electrical charge that can be stored on a capacitor depends on the dimensions of it. So larger capacitors, so larger electrical components, generally speaking, have more capacitance to them. The term capacitance is just the ratio of how much energy can be stored on it to how much voltage is applied to store energy on a capacitor. And we give capacitance by the symbol, the capital letter C. Remember, lowercase c is speed of light. The capital letter C gives capacitance, and that's equal to, and again, this is a ratio, charge stored on a capacitor divided by the voltage applied to the capacitor. In our capacitors, here's a couple of pictures of different capacitors that you might have seen maybe on a circuit board. Sometimes they look like cylinders. You might have little like tabs. That would be the red one in the middle. Some rounded shapes. That would be the yellow and orange ones. For capacitance, units of capacitance are farads, and farads are given by the symbol capital F. And what a farad is a farad is again another ratio, just coulombs per volt. So that ratio of capacitance, charge per voltage, farads, the ratio of coulombs per volt. When we talk about energy stored in capacitors, the reason why we like capacitors and use capacitors is because when we're running electronics, inherently, a lot of the electronics that we use to charge our devices, whether it be an outlet or some sort of battery situation, the voltage and the energy supplied is oftentimes inconsistent. Electricity itself is a reactive sort of system. So typically, when something turns on, everything else that's running at the same time has a little bit of a drop in the amount of energy until the system can react to the new surges to compensate for what's being asked for. So we want to use capacitors to kind of solve this problem. A couple of the main ways we use it. The first one we use is to kind of augment or to kind of like smooth out the voltage applied from whatever voltage supply that we're looking at. So if you have a drop in voltage, a capacitor can step in and kind of compensate and fill the gap. If you got a voltage surge, the energy there generally goes to the capacitor first, or the capacitor takes some of the energy so it doesn't have the ability to overwhelm our circuit. The other spot we use capacitors for, and this is used quite often, is whenever you want a very large voltage discharge in a small amount of time. So use this when you are starting your car. So automobiles have something called starter in them. It takes a lot of energy to get the cycle going in your engine. And we have capacitors there at our starter. That's mostly what a starter is a capacitor. That starts the process, and we need a lot of energy there to get it going. You'll have capacitors in large appliances like washer dryer, in your refrigerator. You'll have capacitors in like your air conditioners. Anything that takes a lot of energy to get going, they can store energy in a capacitor in order to allow it to get that first like kick to get going. We can calculate how much energy is stored in a capacitor a couple different ways, and these equations are in your reference tables. The first one, in the capital U, obviously is energy, potential energy. So the energy of a capacitor is equal to 1/2 times the charge stored on the capacitor multiplied by the voltage applied to the capacitor. Another way to look at it is with capacitance and voltage. So you could say 1/2, and then you have the capacitance of the capacitor, and then you multiply that by the voltage squared. So either one of these equations, depending on your input, can be used to find out how much energy is actually stored on a capacitor. The most common iteration of a capacitor is referred to as a parallel plate capacitor, and it is just what it sounds like. It's two metal plates that are parallel to each other. They connect these in circuits. In a parallel plate capacitor, we really just consider the spaces between the plates. We don't really look at the edge effects, which are a little more uncommon. But if we're looking at the parallel plate capacitor, we can determine how much capacitance is there by looking at the geometry of the capacitor. And here we have another equation, also in your reference table, that we can use to calculate capacitance. we have permittivity of free space, E naught, first term. The A, capital A, is the area of the parallel plates, and D is the distance separating these plates. So if we have the dimensions of a parallel plate capacitor, specifically the area of the plates and the distance between the plates, we can use that in the constant in our reference table to determine what the capacitance of this is. Dielectrics is the last concept I want to talk about in capacitance. And what dielectrics are is they're insulating materials that are used to place between parallel plates that increases the amount of capacitance that something has. Capacitance and increased capacitance is a good thing. Typically, when you buy a capacitor, when a capacitor is in some sort of electrical component, they almost always have dielectrics in them. They both help with the manufacturing and the geometry of it to keep the spacing, but also they make the capacitors a little bit more effective. What the dielectrics do is when they're between the two parallel plates, the parallel plates are able to hold charge because the two different parts, the charge that's on each side of the plate kind of communicates with each other. So if you put the dielectric in between them, they have to do a little bit more work to kind of communicate with each other. This allows more charge to pile up on the capacitors. And the insulator kind of decreases the amount of voltage that any particular amount of charge would act between them. All this has the effect of allowing more charge to be added to the capacitor and increasing, because of the additional charge, because the voltage will stay the same, increasing the amount of energy that can be stored on there. When we're looking at dielectrics, there's a constant, and this is the lowercase k. That's the ratio of the capacitor with and without the dielectric. So if you're looking for the dielectric constant, you take the new capacitance divided by the old capacitance, and it's really just a ratio. It allows us to identify how much better the capacitor is due to the dielectric. So if some capacitor had a capacitance of 5 farads, you put a dielectric between it, and now it has 10 farads, 10 farads being twice as good as 5 farads, so this is an increase in capacitance, right? You have twice as much. Your dielectric constant is 2. If it goes from 5 to 15, your dielectric constant is 3. So dielectric can be used just as a multiplier at how much better it is. If you add your capacitance to a parallel plate capacitor, and this again is in your reference table, you could just augment the equation by including the dielectric constant inside of it. All right, so in your notes, you have a couple different examples of dielectrics and capacitors, and I kind of want to go through them just so you have an idea on how to use this with some of our other electrostatic equations. In this first one, we have a parallel plate capacitor. Right? It has a second capacitor with twice the area and twice the separation as the first capacitor. And we just want to see how this affects the total capacitance. Now, looking at our parallel plate capacitor, we have the equation shown up here based on area and separation of plates. And if in our new capacitor, if we double the area and double the separation between the plates, we have double both the numerator and denominator. That does not affect the amount of capacitance. In this first one, you end up with exactly the same capacitance. So C naught would equal to C, or the original capacitance would equal the final capacitance of our second. In this second example, we have an isolated capacitor with air between its plates, right? So no dielectric. There's a potential difference between them, V naught. There's a charge between them, Q naught. After the space is filled with oil, and oil is a dielectric, the difference in the potential is V and Q, respectively. So what's the relationship between those? We're going to look at this equation right here that says capacitance is equal to charge divided by voltage. Now, with an isolated capacitor, that means there can't be any change in the amount of charge being there because it's isolated. Nothing else can send any charge to the capacitor. So right off the bat, we know that the initial charge is going to be equal to the final charge. So the first two, A and B, are going to be really our only options with an isolated capacitor. But if we do put the dielectric in, and that increases the amount of capacitance here, right, we need to be able to figure out how the voltage must change in order to give that increase of capacitance. So if we have an increase of capacitance and voltage in the denominator, a decrease in the amount of voltage would yield an increase in the total amount of capacitance. And so our answer is B. The charge initial and the charge final are the same, but due to the dielectric and the increase in capacitance, the new voltage must be less than the initial voltage. In this next example, you have a capacitor. A parallel plate capacitor has a charge of plus Q on its plate and negative Q on the other plate. So it has charge Q there. The plates of each have an area A and are distance D apart. So these are parallel plates. You have D and A given, so you can relate this geometrically and by its dimensions. They give a single proton. The single proton has a charge of plus E, and it's released from the positively charged plate, and it arrives at the other plate with a certain amount of kinetic energy. So we have to somehow take this energy out of our parallel or out of our capacitors and get it into our values based on the dimensions. And here we have two different equations that are going to relate capacitance, and they're both true. Based on our parallel plate one, the leftmost one says it's related to the area of the plates and the distance between them. And the right one says that it's related to the charge on the plates and the voltage applied to the plates. Since both of these things are equal to capacitance, we can set these two together. And ultimately, my goal here is to get to the value of voltage, because voltage is a stand-in for energy, because it's just energy divided by charge. That's our voltage. So I'm going to rearrange this one that I have on the right and solve this for voltage, because voltage is equal to charge times D divided by permittivity of free space times the area of the plates. This gives me the voltage on my plate. I know that energy, in this case will be kinetic energy, can be equal to voltage times charge. So really it's this equation we have QD over permittivity times 8 multiplied by the elementary charge. And this gives us a EQD divided by permittivity of free space and divided by the area, cross-sectional area of our